Thank you all for joining us for this second roundtable of the uncertainty quantification in natural hazards engineering working group of the SIM Center. In this specific roundtable, we're going to be discussing surrogate modeling. We have three excellent speakers today with us. So they're all going to have around 12 minutes for their presentations, and then we're going to have at least 40 minutes, hopefully, for discussions at the end. If you have any questions during their presentations, I encourage you to use the Q&A button for those questions. Please do not use a chat. We prefer for this roundtable to use the Q&A function of Zoom. My name is Alexis Taflanidis. I am the working group leader, and also as introduction to the three more specific presentations we're going to see today, I'm going to start with a general overview. So again, for the next 10 minutes, I'm going to go for overview of surrogate modeling for natural hazards risk assessment. So let's motivate our problems. So continuous advances in computer science and high-performance computing are promoting the use of computational intensive high-fidelity numerical models to faithfully simulate real-world processes. So either this is the structure for the hazard. We all love our high-fidelity models. Now, the still challenges exist, though, despite all these computational advances, for adopting such high-fidelity models in many engineering applications that need multiple calls to the expensive numerical model. Uncertainty propagation, what we're going to be discussed today, it's one of them, but you have similar challenges with optimal design, baseline calibration, and so forth. Simply put, doing one simulation, you have the computational budget, but if you need hundreds or thousands, you don't have it anymore. So that creates challenges. So the solution for still being able to leverage and incorporate these high-fidelity models in risk assessment is to use a data-driven approximation. What we call a surrogate model, the other terms that you might have heard is emulator or metamodel. So these are data-driven approximations of the input-output relationship of your numerical model. Frequently, you might hear the term that numerical model being referenced as process, computer code, or simulator, especially in the applied mathematics and computer science field. So, this is, let's say, this sort of the response that comes from the real model. What we're going to do a number of simulations, what we call experiments or training points. For different input configurations, we're going to predict the output. This can be just a single output, or it could be multiple outputs in reality. And then we're going to try to understand the relationship between the input and an output. We're going to try to approximate that relationship that we see from those observations using our preferred type of surrogate model. Now, that surrogate model is going to include some hyperparameter. This is going to be the calibration of the surrogate model. You can select any of the many surrogate models that exist, and ultimately you get the surrogate model approximation of the real surface. Now, your ultimate objective of the surrogate model is to come and replace the original numerical model, so that you can do your calculations much faster. So after calibrated, the cost of the surrogate model is practically, it's very small compared to the original high-fidelity model. Now, I always say this as a caution because I see many people think that surrogate models are panacea, they can solve anything. That's not true. The only thing that they allow you to do is do more simulations at a smaller computational cost. If for whatever reason you cannot solve the exact problem that you want with a high-fidelity model, using a surrogate model is not going to solve it for you either. Now, surrogate model that has engineering, you might think that there are a variety of things that you can have. You can have perhaps for the exposure, so surrogating a NATSIC model for storm surge, or surrogate something related to the earthquakes. Very frequently, or the most typical implementation is you're surrogating the structural model, predictions, and you can also want to surrogate like the damage and loss assessment or the consequence estimation of a complex network. Now, of course, in many times, in NHG natural hazard engineering, you have problems that go across all these three modules. Always the advice is surrogate, like even if you have a process that goes through all these modules, you're only going to surrogate the individual modules, and you're going to focus your surrogate in the most computationally expensive task. So what we call end-to-end surrogates, or in surrogates across multiple modules, they're always going to have reduced accuracy, and they're going to have restricted generalization capabilities. I'm going to explain this a little bit in the next slides. But when you think of the surrogate, you always think, out of all the things that I do in my natural hazard risk assessment, what is the aspects that are the computationally expensive? That's when I'm going to focus on my surrogates. Okay, so a little bit on the surrogate model formulation. You're going to have input X, it can be a vector, you can have an output Z. Again, it can be a vector. So in no reality, your simulator provides the output as the function of the input. So you know your X, you run your simulation, you get your Z. And now, for example, for the X, it could be the excitation feature. It's going to be also the excitation time series itself, material properties, structural model properties, depending on what problem you're looking at. The output, it could be the hazard intensity, it could be the PKDPs, actually it could be a time series of the response, damage indices, traffic delay if you're doing network analysis, and so forth and so forth. So again, I'm going to be using a single input, single output example to demonstrate some of these concepts. So this is sort of the actual response that's going to come from this model. What we're going to do, we're going to select a number of training points. We're going to evaluate the simulator for each of them. This, in no reality, are my observations. So the training points, the input of the training points, and the response of the training point. And then I'm going to calibrate my surrogate model. I was going to select these hyperparameters. I'm going to get those predictions. Now, those predictions are predictions for X, but in no reality, they depend on your database and then depend also on your hyperparameters calibration. So now this is a prediction. Here, I'm going to also bring the response so you can see how good of a job we're doing. Now, another thing we need to remember is that my simulator can have some additional inputs. It could be, for example, the drag coefficient or the parametric wind field model if you're running a NASC. It could be some things related to the structures that you're not interested into varying, for example, dam migration and so forth. In all reality, if you think about it, both your output and therefore the output of the actual model and also the output of the surrogate model is a function of Q. And that also you have to bear in mind. So whatever additional assumptions you made for running the high fidelity model, they come with you into your surrogate model approximation. That's also the reason why we said before, don't try to run end-to-end surrogates, because again, those end-to-end surrogates, when you go over the other modules, they will have some other assumptions for these inputs. And then your surrogate model is married to those assumptions. So and to simplify our notations, I'm going to avoid having carrying here Q. I'm also going to ignore the hyperparameter. So I'm going to look at, the response of my surrogate is for a given X, but remember, it always depends on your database. Now, the question is, okay, what inputs should be varying? Okay, this should be the inputs that you are interested for future analysis scenarios. So, for example, let's say you have a surrogate for some bridges, and you want to change in the future analysis the width of your base or the number of the base, deterministically. Okay, you should include it in X, or you might have some things that have a probabilistic description. Those should define what is the inputs with respect to which you try to develop your surrogate, not these additional guys. And once you have your surrogate, like in risk assessment, you try to calculate some version of risk. It's always going to be given by some integral. When I have integral in this slide, you always should think of, this is a Monte Carlo simulation. Again, that's how we calculate the numerical integrals. In risk assessment, it's going to be a Monte Carlo. I'm still going to present it as an integral, but think of always Monte Carlo. So after you have your surrogate, so these complex integrals, you replace this approximation because your surrogate will have a bias, as you can see here, cannot exactly replicate the actual model. But estimation now of these integrals to Monte Carlo simulation is very efficient because you have a very inexpensive simulator. And one last comment for those you can have deterministic surrogates or you can have probabilistic surrogates. While we probabilistic surrogates or probabilistic machine learning, they also quantify the uncertainty, the predictions originated from the limited observations. The way you do this is either your surrogate is going to be probabilistic, something like a Gaussian process, or you're going to establish this in the calibration of the hyperparameter. So in this case, you'd look something like this. So yeah, I have my mean surrogate predictions, the black, but then I have some quantifications of the error around those predictions. Again, this error quantification is only originated from the fact that we have a limited observation. Now, since we are interested in natural hazards engineering, one common thing we encounter in many natural hazards engineering applications is aleatoric variability. This is what we call stochastic uncertainty. Examples is, hey, the effect of the tidal phases, storm surge simulation, the ground motion variability in earthquakes, realization of random field, and so forth. And so in reality, if you think about it here, our output is a function of both the input and this aleatoric variability. Now, in some cases, you're going to be interested in predicting with respect to aleatoric variability. That's going to be some of the the focus of what Simmer is going to talk about later. Some other cases, though, you don't want to, or perhaps you cannot use W as input to the surrogate model. So this is what Sangri is going to discuss a little bit later in the future. So the question is, hey, then how we address the variability that comes because of W? The very simplest way is, okay, rather than surrogating these complicated guys, just surrogate the statistics of Z under the influence of the aleatoric variability, okay? What it means in this case, yeah, we're going to be surrogating the response. Again, here I'm using expected value. You can do for quantiles, you can do for variance, but always they're going to be defined to some like integral. And in this case, we have our training point. We're actually going to do multiple evaluations for each training point because we are trying to calculate the statistics, and our data is going to be the statistics. Beyond that, this is exactly the same implementation. In reality, this is still a deterministic emulation like I was talking in my previous slide. You just did a little bit more computational effort for calculating the statistics over the training points. And the implementation is the same. You simply end up with an approximation of the statistics. Okay, again, given, of course, the database of the training points. Now, of course, this requires for each training point multiple calculations to calculate the statistics. So the alternative is when you try to, rather than approximate the statistics, approximate directly the distribution. This brings us into the more complicated field of stochastic emulation. So for stochastic emulation, again, your training points are going to be, so you're going to pairing each training point with some realization of the aleatoric variability, and then you, again, single evaluation for each of the training point. And this is interesting. So you view here the database, you don't see W anymore, because again, you don't want your surrogate model to predict with respect to W. So but your observations are going to look like very noisy because they incorporate this aleatoric influence. So what we try here, we try to actually surrogate the actual distribution. The fact that this distribution comes from the fact that it is the impact of W, okay, in reality. So we're going to try to surrogate here. Again, more details on how exactly you do this, Sangri is going to discuss a little bit later. So this is how you end up with. So you can, again, here I'm plotting the mean and some quantiles that come from this surrogate. But one surrogate using only these observations, because it's surrogate in the distribution, can give you all these predictions. And this is how the actual response is looks at. So for when you have this aleatoric variability, you can either do stochastic emulation, which is a little bit more complicated, but it requires fewer number of simulations, or you can actually come and approximate directly the statistics. Propagation of the uncertainty with respect to X is exactly the same way that you do it in the deterministic, case. In other words, here the surrogate is going to give you prediction with respect to X. You're going to propagate the uncertainty with respect to X, total probability theorem, as we saw before. Now, a little bit of discussion of the selection of the input and the output or the surrogate model type. what is the right surrogate model, or for one problem, what is the selection of the input and the output depends a lot on how many simulations you can afford. There's a lot of problems that they have multiple opportunities, and you always need to think, how many simulations can I do, feasibly, and what that tells me about how should I be selecting the input and then the output. For many applications, not for all, in natural science engineering, we can only afford a very limited number of simulations. Let's look at an example. This is going to be an earthquake example. So we're going to run different ground motions we're going to have some uncertainty even in the structural model parameters. And these are our EDPs at different flows that we try to predict. And we're going to use this to actually do, a loss assessment. So the loss assessment, in all reality, it's a simple analytical quantification. And now, if we were trying to do an end-to-end here, I'm going to go back to my previous discussion, all these guys here that are inputs into your loss assessment, they either need to be included on QRX. So that's why it's not a good idea to do this. We always prefer to directly surrogate here so that we don't have additional inputs that impact our surrogate model formulation. In reality, this is the computational intensive part. This is relatively simple to do, so we're not going to include it in our surrogate. But now the question is, okay, what should be our input? What should be our output? Does aleatoric variability exist? You have different options here. So the structural model parameters are definitely going to be part of your input. That's why I have them here red. Now, one option is the actual time series is going to be your input. And then your output is going to be the time series of the EDPs. In this case, probably you have to use like a neural network to be able to capture really well that temporal variability. In fact, you have a ton of data to train. But also it's going to require a larger number of simulations. Depending, of course, this depends on what is the range of excitation intensity, what's the range of structural model parameters. But if you have behavior that goes from linear to grossly nonlinear with excitations that have directivity pulses and non-directivity pulses, you typically need to require a lot of simulations. Now, the other alternative is not to use the whole time series as an input. You're going to come and say, look, I'm going to use some ground motion features. This could be basic intensity measures, or it could be some basis components from the stochastic expansion of your ground motion. And then I'm going to hide everything else, the ground motion variability into the aleatoric. And in this case, your output is not going to be the time history. It's going to be just the peak EDPs. Now, this allows you to consider from a wide range of surrogate models and perhaps even use a fewer simulations, but also you can only predict the distribution of the peaks. You cannot exactly be able to predict exactly the time series response. So if you really want a time series response, your previous option is the only feasibility. If you are okay with predicting perhaps only the ADP distributions, you can hide some things in the aleatoric variability if needed. Now, a few more slides. One quick slide of the design of computer experiments. This is really important. You can go with a space filling. That's a standard implementation. We're going to do, space filling in terms of how you're going to select the training points, or you can do an adaptive sequential implementation. In this case, you use the surrogate that is trained using the current training points to help you select the next batch of experiments. Even so, initially you think, I'm going to do 100 simulations. Rather than doing 100 in one step, you're going to do 50, and then you're going to use the surrogate that is trained using that 50 to help guide the selection of the next 10 based on the best value of information. You're going to use some exploration principles. This is an example so that you can see. So I have my space filling blue training points here. That's my exact surface. That's the approximation I'm going to come and get. And here I'm going to do different versions of adaptive sequential implementation to select the red guys. And you can see, depending on what exactly version you're going to come and use, even here with just additional 10, you have a much better approximation. But this is the benefits of using both a sequential and adaptive implementation. You can call this active learning, but also carefully selecting what are the principles for selection. And really how this DOE is performed, it depends on what you want from your surrogate. So if you're doing a global surrogate, in other words, if you don't know what you're going to use the surrogate for, in other words, you're going to this is going to serve as a global replacement of the original model. Your DOE, design of experiments, implementation is different. If you know what you're going to use the surrogate for, and you want to use a surrogate just to calculate a specific reliability index, then that really comes and changes how your design of a computer experiment is going to be done. And my final slide, some other topics of importance. I'm going to quickly go over this, and we can discuss more at the end. Careful of overfitting or over smoothing, either because you have too many hyperparameters that you can play with in your surrogate model, or you cannot, for some reason, you cannot. Yeah, there is an automatic variability, and you don't capture it well. You end up over smoothing in this case. So appropriate validation is really important, and especially to promote trustworthiness and interpretability. And Norberto is going to talk about it a little bit in his presentation. Do not use a surrogate model to extrapolate. That either on the parametric space, but also with respect to the assumptions and the definitions for both X and W. All of us will really understand, yeah, I shouldn't extrapolate between my training points. But for most of the natural hazards applications, there are some other assumptions that go into in your problem formulation. And be careful not try to extrapolate beyond them, either with respect to how you defined input X or perhaps Q, or also how your aleatoric variability comes and impacts you. DOE is very important, even for global metamodeling applications. So in many of the problems that I have looked at least, in natural hazard engineering, there is a big restriction of the number of simulations you can perform. And that gives an even bigger importance on how you should appropriately select the input and the output. And the number of outputs for many regional applications can be massive, and that has some impacts on the calibration of both the deployment. It's also for regional applications, general applicability and resolution precision, you always need to balance, and it's generally for removing the bias. Multi-fidelity frameworks, are these multi-fidelity surrogate models or multi-fidelity Monte Carlo, are always really helpful. I hope I motivated enough the general discussion. We're going to move next to our three distinguished speakers that they're going to be talking about different hazards, and they're going to have a focus on different types of the surrogate model implementation. I will ask you to hold your questions, and you can use the Q&A feature to ask them right now, or wait until the end of all three next presentations when we're going to open to a broader discussion. With that, Norberto, you can start sharing, and you have the con.
You're muted.
Oh, hello, can you hear me?
Yes, we can.
Yes, can you see the presentation? Not yet.
We see, yes, we see the presentation. Thank you.
Okay, perfect. Yeah, so good morning or good afternoon, everyone. My name is Norberto Nadal Caraballo. I'm a senior research engineer at the U.S. Army Coastal and Hydraulics Laboratory. And the subject of our presentation is surrogate modeling or metamodeling for storm surge hazard quantification. And as a note, all the work discussed in this presentation has been conducted in collaboration with Alex. It's been an ongoing collaboration for more than 10 or so years. So as an introduction, so exposure to coastal storm hazards is related to both uncertainty and risk. And in this context, typically we are either talking about real-time risk assessment, where the uncertainty originates from, for example, forecasting errors in the National Hurricane Center advisory, or we could be referring to long-term risk assessment, where the uncertainty in this case originates from the aleatory occurrence of some hazard scenarios and other factors, such as a mean sea level fluctuation. So in this presentation in particular, I'll be focusing on the work done by the Corps of Engineers and the University of Notre Dame, specifically on the estimation of the long-term risk assessment. So for those of you that might not be entirely familiar with storm surge numerical model simulations, typically we start with a description of the storms along track evolution pertaining, for example, to intensity, size, translational speed, angle of approach. We then create or develop a parametric wind and pressure fields that are used in turn as inputs to drive a numerical model, in our case, that solve shallow water equations. And then we obtain the output of interest, which is typically time series of surge predictions or wave climate predictions across usually very large domains in the order of millions of nodes. And one of the main challenges when relying on high fidelity simulation from models like ATSERC, for example, is that each single simulation for each single storm requires thousands of CPU hours in an HPC. So kind of the good news is that there are already, we have already different coastal flood hazard studies that provide databases of these storm suites and ATSERC simulations for different synthetic storm scenarios. And we can use this information to train surrogate models that Alex mentioned before. So we can leverage these surrogate models to support, for example, storm surge, hazard predictions, decision-making for coastal planners, engineering design of flood protection or flood reductions structures, and we can apply this also for emergency management applications. So surrogate models in our context, again, needs to be developed or established across 3 different domains. And with this, we have the storm parameters or storm features, the spatial domain, and the temporal domain. So in our case, the most important one is the storm features or storm parameters. And there are different complexities that arises from this problem. For example, we typically must rely on just a small number of simulations or relative small number simulation due to the computational burden. We also need to output or produce these results at millions of nodes or point locations. And we have particularly challenges in terms of storm surge when predicting and even when we simulate the wet and dry interface near on the near shore, onshore. So in particular, this wet-dry interface is one of the most important results that we can obtain from this kind of simulation, but it's also the most challenging due to the many different components related to the numerical simulation, but also how that translates into the storm surge surrogate emulation. And to address, for example, we also have the temporal domain, and in this case, it's relatively easier to characterize. Since in the case of storm surge, typically we have a relatively smooth hydrograph or time series of surge. So to address these challenges, typically we calibrate surrogate models taking into account or considering storm surge features and parameters as input, and then storm surge at each node locations at the output. Then we also, in our case, we incorporate a classifier to improve the accuracy of the prediction. And we also adopt a latent space to deal with the challenge of the high dimensionality of the output, and other approaches, other features of our framework is doing imputation to fill in missing data, and also taking into account the spatiotemporal correlation between the outputs. So with respect to the storm parameters, it's very important to have an adequate parameterization of the storms in order to characterize the significant differences from the storms, but also this parameterization needs to be simple enough to avoid over parameterization. So in our case, we accomplished this by using a relatively small number of parameters. And for those of you that might be familiar with the joint probability method, these are essentially the parameters that we carry forward in this analysis. So we consider the landfall or reference location, typically latitude and longitude, the heading direction or angle of approach, central pressure deficit as a proxy for intensity, translation speed, and radius of maximum winds to characterize the size of the storm. And typically we define these parameters either at landfall or at the location of peak strength of the storm, and this varies by study. So a solution specifically to efficiently handle the high dimensional issue of the output is to essentially project to a lower dimension, a low dimension latent space. And it's in this latent space where we can calibrate the surrogate model. We can also establish the data imputation for missing values, and we then calculate the statistics of interest. And then we propagate or project back to the original space. And of course, we can do this using different projection schemes. So in our case, we have a strong preference for PCA, for example, linear projection techniques, because these have been shown to be sufficient due to the high geospatial resolution of the underlying output, in this case, the storm surge. So here we have some additional insights regarding the dimensionality reduction. Typically, we develop a surrogate model for each of the latent components, and this is in order to improve accuracy. And typically, we have around 100, we keep around 100 latent components or less. So the question becomes how many latent how many latent components we need to keep in this analysis. So as you can see here from the red curve, it shows the variance as a function of the number of storms that you include in the analysis. So the larger the number of latent components that we keep, the larger the variance that we can explain for the original data. But if we, on the other hand, look at the green curve, we know that there is a limit for this. So at some point, we can keep adding additional latent components, but the benefit that we are gaining from those diminishes significantly. So this is a very important observation because it shows us the challenges in approximating the higher latent components and also capturing more complex interdependencies. And this is due to the limitations of the reduced set that we usually have to deal with. This is a summary of our surrogate model formulation. Typically, we either develop or start with our existing database. We develop we carry out the imputation for missing values, and in our case, we also do the classification of the nodes. We develop the parameterization of the input of the storm inputs, the storm parameters. We also calibrate a predictive surrogate model as well as a classification surrogate model. We combine both of the results from these metamodels, and this is where the heavy computational burden really exists in this framework. So we can do the calibration of the surrogate models offline, and then we have the benefit that conducting or running the metamodel to do the prediction of the responses for any new storms typically can be done in a matter of seconds. So for the remaining of the presentation, I'm almost running out of time, so I just want to go through some quick results for answering the question if this metamodeling framework really works. And first, I'll be focusing on presenting some results for specific storms, but also from the perspective of regional hazard estimation. So in this case, we have a 2D plot presenting results for the New York, New Jersey area. We have 3 different plots. To the left, we have the actual numerical simulation results. Then we have in the middle Gaussian process or GP using PCA for the latent components. And then we have at the end to the right, we have Gaussian process, but using explicit prediction. So the results are very similar. We can also produce results for entire time series of the storms, and typically the results are quite good. For regional hazard assessment, the workflow is typically or starts typically with the representative storm suite. Then we conduct the high fidelity numerical simulation. We then aggregate the results and we produce ultimately the search hazard maps. Now, when we change this approach to include surrogate modeling, the main goal is to replace a lot of the high fidelity simulations with the surrogate models. So in this context, we use a subset of the storms to train the surrogate model. And then the question that arises is, what are the real benefits of doing this hybrid approach of including high fidelity simulation supported by surrogate models, and how we can conduct smart selection of the storms? So in terms of the mathematical definition of the problem, we have the storm parameters, the recurrence rate. We then compute the hazard curve. But then in this case, when we are using surrogate modeling, we do the simulations for a subset of storms. We train the metamodel. And then in this case, we have this combined representation of the responses where the red values indicate the storm simulated in high fidelity models, and the blue ones are the results from the surrogate model emulation. So we have the benefit when we use a Gaussian process of having or being able to predict the variance of the responses. So when we develop the hazard curve, for example, we can do it in this probabilistic context and do many realizations of these hazard curves. So we can, in the end, estimate not only the mean or a central statistic, but also the confidence bounds. And in this case study, for example, it's for the state of Louisiana. We started with 645 storms. We compared the results considering both a Gaussian process emulation and also more of a brute force Monte Carlo approach. We also compared 2 different approaches for selecting the storms that Alex mentioned before, space filling approach, as well as adaptive selection. We also have the validation metrics. And I think this is my second to last slide. So we have showing the results here on the validation results. On the top row of the results, we have the coefficient of determination for different annual incidence frequencies. And we can see the blue and red curve, which are the Gaussian process aided results, compared to the solid black curve, which is the Monte Carlo results. And for Monte Carlo, you need to get very close to almost the total number of storms that you have in this set, almost 600 storms, to get some decent results. But when we use the Gaussian process, we start getting very good results just by considering 150 to 200 storms. So we also show the improvements that we can obtain by using the adaptive selection. We see some improvements when looking at the red curve compared to the blue ones. And there's also some additional improvements when we consider the probabilistic implementation. So we have some 2D plots comparing the results for the state of Louisiana. The row of plots at the bottom represents the relative results compared to the reference, the result produced with the numerical simulation. And also the results are improved quite significantly when we consider the adaptive implementation of the results. And in terms of the hazard curve, again, with the adaptive selection of storms, looking at the uncertainty, we can see much narrower confidence bounds. And this is the coastal slide for the coastal hazard system. This is the database that we use to train these metamodeling results. I'm sure if there's interest in this, you can reach out to Alex or myself at some point. Yeah, these are my presentation. So I appreciate everyone's time, and yeah, we'll address any questions at the end. Thank you.
Thanks, Norberto. We're going to move next to Sangri. A reminder to everyone, if you have any specific questions during the presentations, you don't need to wait at the end. You can ask them to the speakers using the Q&A function. Sangri, the floor is yours.
Hey, thank you, Alex. Hello, everyone. Thank you so much for joining. I have been software developer at Sim Center for the past 5 years, so I'm really excited to present at this roundtable meeting. So I will talk about how stochastic emulation method can help us to estimate engineering demand parameters for seismic applications. So as Alex gave a really nice overview, stochastic emulators are one of the surrogate modeling methods that is used for stochastic simulators. So that means we have some deterministic parameters as input of our target model. And this model, we're going to produce random outputs. And this randomness comes from various sources of uncertainties that is not explicitly described by these deterministic inputs. And because of that, our surrogate model should also take deterministic values as input and produce a random distribution as its prediction. And this randomness comes from different reasons. It can be non-parametric uncertainty if you are surrogating using real-world observations, but it can also be high-dimensional random variables that used as input of your model, for example, like random field. You don't want to use this random field as the input of surrogate model, sometimes because it's so high dimension. So you just want to let it propagate to your output value and try to capture on the output side. So the seismic application that I want to present today is an example of the second case. So when we have a model and we are often interested in predicting the probability distribution of engineering demand parameters like peak acceleration or peak interstory drifts at each floor. And there are different sources of uncertainty in this system. One is structural uncertainties, which have really nice parametric description in many cases. And also there is excitation uncertainty. And if we introduce something like intensity measures to describe this excitation, then we have some sort of parametric description as well. So we can use something like peak ground acceleration, duration, or frequency information to characterize our time history. But the problem or the fact is that this intensity measures does not give sufficient it's not sufficient in terms of information, meaning you can have 2 ground motions that shares the exact same intensity measure vectors, but their time history can be really different, and this different variability represents motion-to-motion variability, which is the term you use in earthquake engineering. And this variability is a bit more tricky because it does not really offer a good parametric description. So when we try to surrogate this system, there are different ways, but what we often do is to use only these parametric inputs, parametric variables as input of our surrogate. But then we need to acknowledge the fact that we will have variability or uncertainty in our response prediction because we are not explicitly capturing motion-to-motion variability through our input values. So that's why we need stochastic emulation for this type of earthquake problems. And in earthquake engineering, capturing this kind of variability in the output is really important because it concerns high consequence scenarios. And in literature, there are different approaches to achieve these goals, but I really like using Gaussian process model-based approaches because it really captures different sources of uncertainty in a natural and mathematically elegant way. So using Gaussian process model, you can produce two different types of uncertainties. First one is epistemic uncertainty, which is really related to the amount of data, training data that you have. So if you have like a large number of data sets, this uncertainty will gonna practically approach to zero. However, there's another type of uncertainty, which is allometric uncertainties. And this is more related to like inherent data or your system, or it's like the way of formulating your system. So even if you add more and more data set, these bounds will not gonna approach zero. So in practical GP application, the uncertainty bounds that is provided by GP function will be a combination of this epistemic uncertainty, which captures the variability in your signal, underlying signal, and this allometric uncertainty, which describes like true predictive noise in your data set. And as a result, our GP formulation also have two different components. First is signal part, and second is noise part. And the type of variability that I was explaining before is really related to this noise component. Especially, we are interested in the level of variance that it produces. So it predicts. So in traditional GP formulation, they use a constant variable tau to represent the level of variability in your data set across entire domain. And it's a bit restrictive. So because this means even when you have different parameter inputs, your predictive variance will always be the same, which is not very realistic in many cases. So if your data look like either this curve or this curve, then they are not, their variance is not constant across the domain, so traditional GP model cannot be used. Instead, stochastic emulation method can be used. So mathematically speaking, the only difference to the traditional formulation is the fact that this tau is now need to be a function of x instead of just a constant value. And this gives us lots of more flexibility on the variability that we can capture. And our seismic application is an example that requires those flexibility. So I'm showing you to show that I'm showing you a figure that's taken from this paper. It's really showing you how the response of the structure of displacement and acceleration will gonna change as your excitation intensity varies. And one thing you can notice is the fact that their variability is not constant across the domain. Especially if you see this acceleration result, you see the variability increases and then it starts to decrease at some point. So we don't want to use this constant variance model to predict these responses. And in literature, to capture this flexible shape of variance, what we do typically is to introduce another layer of surrogate that tries to capture only the variability inside your data sets and use as some preliminary information to train your main surrogate model. And there are different ways of trying to capturing those variability. One way is to rely on replication strategy. Here, replication means in your training data set, there are multiple training points that shares the exact same inputs. And if you have those points, you can really understand the underlying variability that's coming from your data set. And if you have these replication points at different point locations of your parametric domain, then you can really interpolate this variability to estimate your underlying variance function. However, it's a bit more expensive, and also there are many practical problems where you actually don't have control over selecting the training points. So you just need to use existing training points to create this type of surrogate. So in that case, we will require a so-called no replication strategy. And again, there are different ways of doing it. And one way is to predict the mean first, and then predict the variability, and then predict the entire distribution. So to give you a better idea, I'm going to show you a flow chart. So we start by a training data set that does not have replication points. So the first thing we do is to create a surrogate model, which we call tertiary surrogate model, that tries to capture only the mean part of your data set. And once you have approximated your mean function, you can see how each of these samples are deviated from your mean function, and then collect those sample deviation values so that it can be used to learn underlying variance function of your data set. So we call this surrogate, which approximate the level of variability as secondary surrogate. And using this function as a skeleton, you can now train a primary surrogate, which in this case was a heteroscedastic Gaussian process model, to optimize your final prediction of mean and variance of your data set, of your new prediction points. So in that way, now we have a way of capturing the variability in your data set. And the problem is that in our problem, there was not enough because there were correlations in the data set that's coming from aleatoric uncertainty. So that means given your input parameters, if your acceleration realization is larger than predicted mean, it is likely that your displacement is also larger. And if we train independent surrogate for different outputs, and if we don't consider their covariance or correlations, that means we are losing information, something like drift sensitive and acceleration sensitive components are likely to either fail together or survive together. And this can really underestimate the final risk prediction. So there was a need for us as a sim center to improve those algorithms so that it can also capture the underlying correlation of this data set. And luckily, that was really straightforward. So our goal now is to predict the entire covariance matrix instead of just the variance of each output. And if you go back to our algorithm, there are parts where it was used to predict the level of variability across the domain. And this part simply need to be modified to predict the covariance matrix of the underlying domain for multiple outputs. So instead of collecting sample deviation from the mean, we are looking at not only sample deviation at each dimension, but we are also looking at cross deviation of like two dimension pairs. It is straightforward, but we need to be cautious on one thing of the fact that now the prediction of our covariance matrix, which comes from the secondary surrogate, need to somehow ensure positive definiteness. So to do this, we introduced some tricks like constraining the hyperparameters of GP that is used to predict each of these parameters. And also we added final projection or correction step to make sure that our final prediction will gonna be positive definite. And then we needed to validate those developed algorithms using some numerical examples. We had 3-story structure model with 12 parameters. Some of them are structure and others are excitation parameters. And we were trying to predict the response of at each floors. And we generated reference cases using 1,000 test samples, and for each of them, we compared predicted distribution with the reference distribution using KL divergence. And I'm showing the result box bound for like 30 different independent simulations with different random seeds to show how robust those methods are. And I'm showing the result for, accuracy, prediction accuracy for replication strategy versus non-replication strategy. And we were playing with different configurations like percentage of samples with no replication. And as a result, what we saw is that when it's 100% no replication, meaning all the training points are unique, we are really getting best performance compared to outperforming the existing approaches. And great thing is that this is not really restricted. We really expanded the applicable class of problems by not requiring replications anymore. And we tried with different training sizes and configurations, and we saw the same trend. And the previous results were marginal distributions, so we also looked at joint distribution, and the trend was exactly the same. So when we have no replication strategy, we still have very stable prediction when we constrain the amount of computational cost for all different cases. And finally, and the most importantly, we plugged in our validated surrogate model to practical or earthquake engineer problem that really matters. So we assign probability distributions to the input of our surrogate model, and then try to compare the vulnerability distribution and seismic loss distribution, and then compare it with the reference value. And we have really good agreement between these two prediction and the reference values. And this tells us that our surrogate model is ready to be used in some of the serious earthquake engineering problems. As a summary, I introduced you what is stochastic emulation model and how we can train stochastic emulator using without any replications, and how it can be extended to multi-output correlations. And I believe the stochastic emulation will have increasing, more and more increasing utility in our field as we acknowledge more of uncertainties when we do this natural hazard analysis. So that's the end of my presentation.
Thank you, Shagri. I will really remind everyone, if you have questions, use the Q&A button. And our next and following presentation is going to be given by Simur. Simur, the floor is yours.
Yes, thank you, Alex. Let me share my screen here, make sure everyone is seeing the slides. All right, is everyone seeing the slides?
Are you good?
Okay, very good. Let me just get this out of the way a minute. Okay, so we can get underway here. So with these slides, what I want to do is briefly go through machine learning surrogates for rapid stochastic trajectory prediction in nonlinear structures subject to extreme wind. So before I start, I would just like to acknowledge that this work was carried out by myself and my former PhD student and postdoc, Bo-Wei Lee, who is currently an assistant professor at Texas Tech University. So motivation for this work comes from the extreme responses we can see when we subject structures, for example, to extreme winds. Basically, what we end up with is complex nonlinear structural behavior. And if we want to try and assess these systems in terms of state-of-the-art performance-based design or similar, basically what we need to do is consider this stochastic dynamic responses, because these extreme events, they basically represent a general stochastic excitation propagates through a nonlinear system. So in order to be able to really estimate the performance of these systems, we really ideally would just like the entire stochastic dynamic response. But this is a computationally extremely challenging problem. So the basic idea behind these surrogates was to use AI for predicting the response of the stochastic response to directories. All right, so these approaches are kind of grounded in observing that a structural system in general can be seen as a high-dimensional multi-input, multi-output system. Therefore, a mapping between some high-dimensional stochastic excitation and some high-dimensional stochastic output here indicated with Y. One thing I would like to observe here is that if you're looking at wind like we are in this presentation, this stochastic input here is going to be a multivariate, high-dimensional multivariate stochastic process, which we generally assume to be stationary, but the work I'm going to be presenting here for the surrogates does not require this excitation to be stationary. But it is multivariate, so it's a multivariate stochastic excitation. Now, the first step that we've been implementing in developing these surrogates is actually to define an associated reduced space with respect to the high-dimensional system. Therefore, we then have a mapping or a system that is relating some reduced stochastic input to some reduced stochastic output over here. Now, what we want to do is, instead of trying to solve this reduced model, which is a classic way of solving a reduced space problem, what we want to do is go ahead and learn the mapping between the reduced input and the reduced output using deep learning. And that's where these surrogates are capable of predicting the stochastic output of these systems comes from. All right, so if we want to do something like this, obviously the first step is to identify this reduced basis, and therefore the reduced space. To do that, what you can use, what we've been using in our work is a linear projection. So we've been using proper orthogonal decomposition. Basically, you have a whole series of high-dimensional stochastic inputs, and you can run that high-dimensional model. Therefore, you're going to get some outputs. So these outputs, what you're going to do is construct a snapshots matrix, and then you can carry out a singular value decomposition on that. So basically what you do is represent these responses in terms of some orthogonal basis functions, which are here phi, as well as some singular values. Now, taking advantage of how when you do a singular value decomposition, the majority of the energy of the system will actually be defined by the first few orthogonal basis functions and singular values, you can go ahead and you can define a reduce space for your system here, phi hat, by just taking the first few orthogonal basis functions. All right, so at this point, one's got a way, if one in particular uses a Glarkin projection to define using the same basis functions the reduced input, you've got some reduced input and you've got some reduced output. So the problem becomes one of relating the reduced input to the reduced output. As I said previously, if you're doing classic reduced order modeling, you can try and directly solve this relationship through projecting the entire equation of motion. However, that doesn't generally bring particular computational gains, as you generally do have to, at each time step, return to the high-dimensional space to evaluate the nonlinear restoring forces. So the idea here is to try and use deep learning to actually learn the relationship between this reduced stochastic input and the reduced stochastic output. Now, some things that we have observed is that it's actually convenient to first transform both your reduced input as well as your reduced output into sequences of wavelet coefficients. This simply makes the sequence learning problem, as you are trying to learn something in time, makes it much shorter if you're learning the wavelet coefficients instead of the original time series. So at this point, once you've transformed your reduced input and your reduced output into sequences of wavelet coefficients, the problem becomes one of learning the relationship between the wavelet coefficients associated with the reduced input and the wavelet coefficients associated with the reduced output. And here, once again, what we want to do is use deep learning neural networks. Now, this is a sequence-to-sequence learning problem. So you're going to have to use some type of recurrent neural network to do this. we've been looking at a couple in general. So we've been looking at long short-term memories, so LSTMs, as well as GRUs. We've been looking at other approaches to doing this, including neural operators and physics-informed methods, but I'm going to focus today on some results that we have obtained using LSTMs. Now, the need for a recurrent neural network for these sequence-to-sequence learning problems comes from avoiding gradient exploding and vanishing problems when you're trying to learn something which has a dependency in time. All right, so that's the general structure of the methods that we've been developing. So I'm going to go ahead and show a quick case study here. So what we have is a 37-story steel moment-resisting frame that is assumed to be located in New York City. We've got a high-fidelity model of this frame. So the frame is represented here. We have a high-fidelity model of this. This was developed or created in OpenSeas. It's a fiber-based model, so it's got distributed plasticity, 5 integration points per element. With respect to the wind hazard, we're going to capture wind directionality by considering a sector-by-sector approach. And then to model this multivariate stochastic input of representing the wind excitations, we are considering a wind tunnel informed stochastic wind load model. This is the model based on spectral propositional decomposition. By calibrating that to wind tunnel data, you're going to capture phenomena such as detached flow, vortex shedding. Basically, you will capture whatever you see in the wind tunnel, you're going to capture in your stochastic wind load model. That's going to be the inputs. Once you apply that stochastic input to your system, you get stochastic outputs. The basic idea here of the surrogate is to learn the stochastic outputs for any realization of this multivariate stochastic input. Now, I would like to highlight that this model is a wind tunnel informed stochastic wind load model. We've created this for both wind loads as well as wind pressures. For the wind pressures, you can capture non-Gaussian features as well. All of these models have been implemented in WeUQ. So if you go into WeUQ, you can find the stochastic wind load models that I am using in this application here. Also, for more information on these models, you can actually refer to the paper which is cited below. So in WeUQ, we actually do have the capability of using these models with your own set of data, wind tunnel data, or using the wind tunnel data that is available on WeUQ. So we have got links to various databases of wind tunnel data for you to use. All right, so that's our stochastic input and our general setup. To train these models, what we were interested in is stochastic response predictions for a non-directional mean hourly wind speed at New York for an archetype building of around 56 meters per second that had a mean recurrence interval of about 10,000 years. The structure was designed to be elastic with a wind of around 1,700 years. So we're expecting significant inelasticity to occur here. And we've got a prediction horizon of 1 hour. So we're trying to predict 1 hour of stochastic output using our surrogate model. Wind directionality for the sector-by-sector approach. We had directionality coefficients provided by CPP, who was the wind tunnel consultant who gave us the wind tunnel data. And these were specific for New York City. So we can actually observe within our problem and our surroundings, we had a certain amount of symmetry. Therefore, we actually only had to learn the stochastic outputs for winds between 0 and 90 and 270 and 250. So looking at this kind of wind rows up here, our building sort of in the middle here, we really only needed to consider this top half. Once we've learned that, we will be able to predict the response for the remaining wind angles. So for each wind direction, so in total, we have 19 wind directions. We considered 43 stochastic wind load samples for each wind direction of these 19 wind directions. So we had in total 819 training samples. Now, interestingly, we were training this model on a reduced time horizon. So we're going to train this on 10-minute wind events and then predict 1 hour wind events. So it makes creating this training data far more efficient. Three-dimensional reduced space was sufficient. It captured 99.99% of the energy of the system. So here, what we did, we used an LSTM layer, 200 hidden units, had a dropout probability of 50%. 750 of these training samples were used for training, with 67 used for validation. We used the classic Adam algorithm with a constant learning rate. This is just a quick figure of what the training loss, validation loss look like, which gives an indication that we haven't got any overfitting. So let's take a look at some results. This is performance in training. So what we're looking at is just one response, horizontal response at the top of the building. So what we can see here, this is a time history response for a representative sample in training. You got your blue time history, stochastic output references in blue, and then the dashed red line is the predicted stochastic output. As you can see, this entire stochastic excitation over this 600 seconds, so this 10 minutes, is really well predicted. So you're predicting the entire nonlinear stochastic response of the system. And this is just for one sample. This is the error. So you've got no error accumulation over these 10 minutes. Now, obviously, this is just for one sample. On this plot here, what you have are the peak absolute values coming from these time histories. So these would be your engineering demand parameters. These are estimated from the high fidelity model using the same stochastic input. This is the prediction of those engineering demand parameters from our surrogate model. As you can see, they're all on the 1-1 line, showing that we got really good prediction capability over all samples. These are for various wind directions as well. Here we've got a table just indicating all the wind directions that were considered in training. So you can see we get good prediction over all wind directions. That's just one response. Keep in mind, these are global surrogate models that give you responses at all degrees of freedom simultaneously. So for example, you could be looking at the vertical displacements at that node, you get exactly the same performance. You're looking at rotations at that node, you get exactly the same performance. You can go ahead and look at a different node. Once again, reference in blue. Dash red line is the metamodel. This is just a generic stochastic input, and we're predicting the stochastic output. And we're getting, once again, really good predictions and horizontal, vertical, and rotations. All of these outputs are simultaneously available. And you can even go down to the level of predicting your fiber responses. So this is the stress and strain in a fiber at the bottom of the structure. So up here you've got your time histories with stochastic trajectories in terms of stresses and strains in that fiber. Again, really good prediction. If you're looking here, you've got your hysteretic curves you can look at. Red is your prediction, blue was the true hysteretic curve. And again, here looking at of all samples used in training, looking at the predicted peak absolute value of strain. Horizontal axis is high fidelity model, vertical is a surrogate. So you're getting really good prediction. All right, this is in training. So you'd say, well, okay, training is one thing. We actually want to do this in prediction. Therefore, considering a whole bunch of stochastic inputs that the system has not seen, how does this work? These are the results. We're looking at that top floor displacement. Once again, we've got horizontal displacements, vertical displacements, rotations. If you look, you can see now that we are predicting over an entire hour. If you look here, we can see we're looking at an entire hour, 0 to 3,600 seconds. Red is the metamodel of this nonlinear stochastic output, and blue is the reference. You can see really good correspondence. All right. Here in reality, we are doing a sector by sector. So this is actually stochastic responses for all winds blowing in this easterly sector shown here. So you've got randomness in the wind direction in the sector, and we're predicting these nonlinear stochastic response trajectories. These plots here, this is obviously the time history, is just for one sample, but these plots, once again, looking at the peak absolute response in terms of vertical displacements, horizontal displacements, and rotations. Horizontal axes are the true values coming from running the same stochastic excitations through the high fidelity model. Vertical is the prediction from the surrogate model. We can see everything is basically on the 1-1 line, so we're getting, again, really good prediction of the entire set that we were using. And again, this is purely in prediction, so the system had not seen these stochastic excitations before we made these predictions. Again, no accumulation of error. So if you look at the error plot here, so this is the error plots, we've got no accumulation of error over time. So if we go ahead here, we can look at a different node. So again, really good predictions. This is just a different node, horizontal, vertical, and rotations, getting really similar behavior. You can once again look at fiber responses. So again, we're getting really good prediction even at the level of the fibers. And again, this is for wind directions that are randomly generated within this easterly sector for a 1 hour prediction window. Okay, finally, I would just like to note that if you can predict the stochastic outputs of a system, like we're doing here, for randomly generated input, what you can do is apply methods like the sector by sector approach to get the failure probability of the system independently of wind direction. So an approach like that simply requires you to go ahead and estimate the probability of failure in all sectors, and then just take the maximum probability of failure as the probability of failure of the system. Now to do this, the 3 sectors which were important for this system was east, north, and southwest. So we generated a huge number of samples in the east, north, and southwest sectors, and went ahead and evaluated the system response and got the distribution functions, basically. So what does this end up looking like? These are distribution functions of peak interstory drift at the 20th floor and on the 37th floor. That will be on the right-hand side. So here, what we're doing is we're not assuming any distribution functions. We're just using the output from the surrogate model and constructing the distributions. So reference values are in blue. We ran this also through the high fidelity model for validation. Then we have in red lines are going to be our metamodel. And we can see these are for the 3 critical sectors. We can see really good correspondence all the way down here to 10 to the power of -5. Same thing over here for the response on the 37th floor. Failure probability of system is just the envelope over all sectors. So we're predicting that very well. If you look at residual deformations, so you're really looking at the inelasticity here, you get similar results. So very good prediction of the residual deformation. This is residual drift at the 20th and at the 37th floor for these critical sectors, estimated once again from the surrogate model. So as just a quick concluding remark here, I would like to say that these LSTM networks were employed as surrogates to predict the nonlinear dynamic response of systems subject to general stochastic wind excitation. We have absolutely no assumptions on what that stochastic excitation could be. So it can be stationary, non-stationary, etc. Some of the things we're currently focusing on is actually trying to include physics, so to reduce the amount of samples you need for training, incorporation of nonlinear projection schemes, as well as reduction model schemes that do not, as well as different methods that do not require reduced order models at all. So here we've been working with neural operators. So here I just have a few references. These are the key references for anyone who's interested in this, where all these models were developed. And I'd just like to mention that I showed examples of wind engineering here. You may well be interested in whether you could apply this to seismic excitations. So these 3 papers, which I've just highlighted, all have seismic applications together with the wind applications, as these methods can be equally applied to nonlinear response estimation of seismically excited systems as we use them for wind excited systems here. So with that, I've concluded, and I will yield the floor to Alex.
Yeah, thanks, Seymour. Gonna quickly wrap up with a few slides coming from the Sim Center, and then I'm gonna open to questions. As a reminder, you can ask your questions in the Q&A. We have, let's see, I'm gonna try to share the correct. Some of the questions we already have answered. So thank to all the speakers for these great presentations. Some reminder of the ongoing work from the Sim Center on the world of surrogate modeling. So there are tools for creating general purpose surrogate models. Also, there is a great work being done on establishing application driven surrogate models, and the incorporation of all these different type of surrogate models across all the different modules. The future vision of the Sim Center is that this hazard estimation, especially using high fidelity models across all the different characterizations, will need to deploy surrogate modeling. And also the Sim Center is looking the next phase on try to establish better, communication across the different users and create shared a library of surrogate models. You feel free to get more involved with the Sim Center, either with the working groups or with the community roundtables. And this is just a list of the upcoming roundtables from the different working groups in April. As a reminder, all the roundtable discussions are available on the web, and some future workshops. Also, those of you that really like some of the discussion, there is a mini symposium that further addresses some of these comments in both EMI 2025 and ICOSAR 2025. And with that, I would like to go back and thank all the three speakers that joined us today, and all of you that spent the last 1 hour and 30 minutes. And I will have some time, so I will go back to some of the questions that have been asked in the Q&A. Again, some of the questions that have already been answered, I invite all of them to visit those answers. I'm going to ask one. I think this is for Simur, which did not have. Simur, I see that you try right now to answer it. I'll directly throw it at you. This question goes for Simur. Did you include the local response at the fiber level in the training of the neural network, or did you apply the surrogate model predictions of the nodal degrees of freedom to the fiber section beam column elements to calculate the fiber responses?
Yeah, that's a good question from Joel. So yeah, we actually estimated the response of the elements at the degrees of freedom. So each element has 6 degrees of freedom at each node. So basically you end up with surrogating those degrees of freedom at the ends of the member, and then you can back calculate the fibers. So you don't need to include that fiber responses in your training.
Okay. Another question, which is actually really interesting. What do you see as the most pressing research challenges or open problems in surrogate modeling and uncertainty quantification? We can have probably like a 3-hour discussion on this. I'll offer a really, quick remark, and I'm going to open it to some of the other presenters if they're gonna have any additional questions. I will say that I'm not going to try to sound negative, but one of the biggest challenges is, for me at least, is not treating surrogate models as black boxes. So, we've seen over and over like the sort of the black adoption of the surrogate model without really understanding of the pitfalls of oversmoothing, overfitting, having wrong assumptions. And because there is a lot of, as we've shown, like a lot of mathematics, a lot of optimization, linear algebra behind of all these things. And many times we are just, we see people just go and adopt them as a black boxes that don't validate it correctly. And over my years, I see a more and more increased tendency to jump at the end of the, hey, let's use the surrogate model. Let's skip all the intermediate steps of understanding how it's being used. So I'm also seeing the other problem in computer science coming and deploying the surrogate models without really understanding the physical parts of the problem. So we see some results that really don't make any physical sense. So the biggest challenge is to be patient enough, especially for younger PhD students, to learn completely the fundamentals of both the modeling of the problem and also some of the aspects of the machine learning before going and deploying the machine learning tool on a problem. That's my perspective. I'm going to open to anyone else that wants to offer any additional opinion.
No, happy just to add, I completely agree with you, Alex. I would just add one thing. You can basically create a surrogate model for virtually anything. The only problem is it'll only work for that one specific problem. One of the biggest difficulties is generalization. If you have a specific application in mind, you can always construct something which will work really well. But you can't assume that you can take that and then just use it for everything. It can be actually quite a minor change, which causes your surrogate model to not really work at all. So that having that sensitivity, and I don't think that comes out a lot in the works and the publications you see on surrogate modeling, where someone is showing only a specific problem and it's working really well. But there is a lot of complexity in making them work for a specific problem. And if they work for one specific problem, they cannot work for something very small. Like in the case I was showing, if you change the material model, doesn't necessarily mean that that surrogate model will work. Maybe you're going to have to change the way it's set up just because you changed the causative relationship of the material. So it is definitely complex in that sense.
In my experience, when I was working in SimCenter, the biggest challenges come from the fact that we are trying to solve really difficult problems like high dimensionality of stochastic output, their correlations, but using only limited number of data sets. So we are so there are many physical constraints in amount of data that we can obtain. And so there is only the limitation of the performance, what we can do as a purely data-driven approach. But this is, I think, the point where this engineering insight that we have in our field can really come in to help. Something like introducing reduced order model combined with surrogate or physics combined approaches. I think those will gonna have more and more promising applications in the upcoming years.
Roberto, do you have anything to add, or you think we were covered?
Yeah, no, nothing to add. I think we covered them well.
Okay. There's another, future vision question, but I will pause and see in case everyone other they can unmute and offer some perspective of there is a different question, but else we're gonna go to spend the last few minutes of discussing the future vision question. Okay, the future vision question is, where do you think the field is heading in the next 5-10 years? Are there emerging areas we should focus, physics informed machine learning, hybrid digital twin approaches, and so forth? So anyone wants to take the first crack on this? Again, like very future vision, where are we going?
Yeah, I can comment on that. So at least we have certainly different like expectations or goals in the future. Like in our case, challenge is always the dry node interface, or how do we handle the incorporation of flood protection structures? How do we account in the model for like the build up of some of the features? And this is at the forefront of our wish list in how to handle that. And of course, we have the issues that the people that are kind of handling those situations, it's always for a very small number of locations. So there are challenges in this scaling up those results where we need them to be, of course. And yeah, I think the physics informed machine learning in the case of storm surge and flood simulations, it's something that many people are trying to achieve with different degrees of success at this point.
Quick comment from me. We see a lot of emergence of, like these AI techniques that come from computer science, and they have tremendous potential on addressing real, some of our challenging problems. But I always caution people, like, there is some danger of throwing all of these ideas to every single problem. Not every single problem needs it, and you have to be careful to validate the assumptions of your problem versus the assumptions of your surrogate. But definitely, as long as you can validate them correctly, the incorporation of these AI techniques into the structural engineering has tremendous opportunities.
If I see in the future, we're going to be able to solve many more problems. So these things have got much more robust over time. So we're going to be able to solve a much larger portfolio of problems if they're tuned properly. I think the tuning and understanding of calibration is going to get more and more complex. I think the integration of these methods into more traditional approaches will actually become more common. So we have some very good legacy algorithms for solving problems. Those can be significantly sped up if you have these type of approaches inside them. And so you have a mixture. And it's a bit like multi-fidelity simulation, actually, when you're doing uncertainty propagation. You're trying to use a mixture of what you think your ground truth is and these types of approaches. I think that's going to happen more and more as we move forward. But I do think machine learning, I think people are going to have to get a little bit more comfortable with how machine learning in reality is based on linear algebra. And so really, you've got to kind of get back to the basics and understand the mathematics behind it, because in reality, lots of time you have lots of different methods with lots of different fancy names. And if you look at the actual underneath the hood, they have a lot more similarity to them than maybe appears on the outside. So I think once we move forward and as a community, we start to really understand these approaches more and maybe be a little bit more skeptical of their use instead of sort of, oh, here's a new thing and it's exciting and I can apply it. But I hope we will moving forward, we'll become more and more experts actually in applying these methods and potentially even developing them.
A quick point is that so far when we tried to do a surrogate research, we had very well-defined training sets in open cases and test data sets so that we can take it and use it to create our surrogate. But more and more I see very large-scale models and complex models that makes us hard to obtain those training and test that even. So in the future, I feel like there is some role that surrogate can take place in facilitating generation of this training set of the model by helping them to accelerate the model simulation itself by introducing surrogate in part of this like complex model simulation, and also helping design of experiments from really early stages of this model development. So that's one thing I wanted to add.
Okay, with that, I think we have reached the end of our 1 hour and 30 minutes. I'll put again the advertisement for the next roundtable discussions from the SIM Center, and I'll invite everyone to join me in thanking our 3 excellent speakers for the day, Sabrina, Roberto, and Simur. Thank you very much for sharing your opinions with this community today.
Thank you for the opportunity.
Yeah, thank you, Alex. Thank you, everybody, and make sure to check out the Sim Center if you want.
Take care.